Today I'm going to be talking about sampling unstructured data and interactive visualization. Before I begin, I want to note that the sampling of unstructured data is implemented in ParaView, but we also write a separate sampler, so just keep that in mind, and I'll explain why we have a separate one later in the talk. Regarding the interactive visualization, this includes loading your models into a browser and sharing videos that are made from those models. So let's begin. Many parts of this project are a work in progress, and therefore this NSF project here. So the goal of this project is to create integrated geodynamic reference models for the Earth, and part of that will be data visualization. So in particular, we're going to be talking about sampling of AMR data, which is adaptive mesh refinement. Furthermore, we're going to talk about videos and interactive visualization tests, so feel free to check out this website for more information. Okay, back to this. So specifically, we want to improve I/O and rendering of large data sets. So data visualization is, of course, a crucial part of geodynamics. Whenever you run a model, you want to be able to see it, to make sure everything looks good, and to share it with others. The solution files that Aspect generates, usually these are like VTU files, can be quite large and difficult to load into tools such as ParaView due to memory and rendering times. So in order to help with this issue, we can sample from an unstructured grid to a structured grid. We lose some quality, but benefit from lower storage requirements. So there are different file types to describe unstructured and structured geometries. So what structured data means is your geometry and your triangulation are defined implicitly, meaning you don't have to say where each point is explicitly, and you don't have to specify exactly how your cells look because they're defined implicitly by just the extent, the origin, and the spacing. So, for example, if you have uniform spacing along each axis, X, Y, Z, so structured data can be represented by VTI files. And unstructured data, you have to explicitly specify your points and cells. This is useful for preserving information when we have something like an adaptively refined mesh. And Aspect, of course, generates these. You've probably seen the VTU files generated. If you have a mesh that's structured, so that can be defined implicitly based on extent, origin, and spacing. Of course, an unstructured storage format requires redundant storage because you're basically saying exactly where each point and cell is instead of just saying, this is my spacing, this is my extent and origin, and leaving it at that. So this can, of course, require more memory and cause some issues when rendering in ParaView. Structured data loses information that you gain from adaptive refinement, for example, and curved geometries cannot be exactly represented. So we want to explore, well, why would we use structured data if we lose all this information? Let me describe the idea of sampling. Given unstructured data, and form a structured grid. For each vertex or point of the structured grid, just take on the value of the nearest neighbor. And by take on the value, I mean the value of the field you're interested in. So this can include strain rate or mesh displacement or other fields. This is a constant interpolation. You could use other interpolants, but we haven't gotten around to implementing that, and it's unclear how much better it looks depending on which interpolant you use. This picture shows how the idea of sampling works. For the black lines, this is your unstructured mesh. The red X's are the unstructured points that you have, and then the blue circles are the vertices of the structured grid. Notice that here the vertices of the structured grids, the blue circles, are the same distance apart along each axis. Anyway, for each of the blue circles, you just find the closest unstructured point and take on those values for the field you're interested in. So this is the idea of sampling. We're going to be using the NSYNCR benchmark to compare the results of the structured output versus the unstructured output. This benchmark can be found in Aspect. We have a structured netcdf file versus an unstructured VTU file, and we should note that the structured netcdf file is uncompressed, whereas the unstructured VTU file is compressed. And we'll be looking at rendering as well as various resolutions when it comes to the structured data. So here is what the unstructured output looks like. Notice this is unstructured because we have an adaptively refined mesh, right? If you look near this sinker here, see that these cells are much smaller than the cells, say, over here. So we have adaptive refinement, and this is the unstructured output with various types of rendering. Here is the structured output. Notice that the spacing is uniform across each axis, and the resolutions are different here, right? It seems like we preserve a lot of the information we want. We can see where the sinkers are, and they look pretty comparable. So here are the results we have regarding file size and rendering times of the uncompressed structured information and the unstructured compressed information. Notice in the first table, if we look at the last row, this is at a high resolution, and the file size is 6,480 megabytes, right? But look at the ParaView memory requirement compared to, say, here, where the file size is quite small in comparison, but the ParaView memory requirement is much larger. Another thing to notice is the rendering times. If you look in this row, levels 9, resolution 256, the rendering time here is 0.23 volume renders per second, and then here it's 15, 30. So we see that the rendering times are orders of magnitude quicker for the structured output. So that gives us a reason to sample onto a structured grid. And of course, if we were having trouble with these large file sizes, we have two options when sampling. We can sample onto a coarser grid and just know that we might lose some information there, or um, we could always compress the netcdf file. So again, um, the file sizes for the uncompressed structured data can be larger if we're sampling with very small spacing across each axis. But at the same time, we win when it comes to rendering times and ParaView memory consumption. So this gives us a reason to sample onto a structured grid. This is just a demonstration of like how you can deal with the large file sizes that you may have when sampling onto a structured grid. An easy way is just switch from a double to a float, since likely if, say, your sampled and unsampled outputs differ, it probably doesn't come down to whether you're using double versus float format. So it's an easy way to reduce the file size. As I said at the beginning of the talk, ParaView has a tool to sample from unstructured to structured grids. It's resample to image, but you can only resample with like Cartesian coordinates. So um, some step size in X, some step size in Y, some step size in Z. You can't do lat long depth. And this leads to sampled spherical models having these rectangular blocks. And I have a picture on the next slide. Another issue is you have to load the VTU or unstructured file first before you apply the filter. So this can be limiting in that what if your VTU file is too large to load into ParaView in the first place? Um, so ideally, what we would want to do is work directly from the intermediate file format that aspect can generate. So this is the deal2 intermediate file format. It's a .pd2 file. Ideally, we would be able to sample the PD2 file directly onto a structured grid, so we don't have to load it into ParaView before running the sampling filter. So here's just what the ParaView resampling looks like when you use it on a spherical model. And notice, as I was saying, this is supposed to be just, a smooth sphere, but you end up with these blocks because ParaView only allows resampling onto in a Cartesian space, XYZ. So this is a work in progress. This is the deal2 aspect sampler. And this samples from unstructured to structured, just like the ParaView filter, but here we have support for spherical objects and that you won't get the rectangular blocks because we allow sampling with lat long depth instead of X, Y, Z. So here's just a quick example. This is just a toy problem. It's, I think, step 40 in deal2, and I just made the boundary be some smooth function. So on the top, you have the unstructured output. On the bottom, you have the structured output. And the structured output is structured in the sense that you have an equal step size with respect to um, your radius and your thetas and your phis. Um, so the top is the unstructured. You can see the differences, say, around here and here versus here and here. Another motivation for writing a separate sampler is for the purpose of mesh displacement. So the sampler works with deformed meshes, and you can play around with it by setting the output mesh displacement to be equal to true and set output undeformed mesh to be equal to true. You sample onto a structured grid, so this also samples your mesh displacement field that you're setting to output here. And then you can apply warp by vector in order to get your deformed mesh. And I'll show some examples in the next slide and also on ParaView. This is just a demonstration of the application of the sampler onto the unstructured output here. This is the structured output, and it's run at a very coarse resolution for the bottom. The field that's being output is the strain rate. Here, this is our reference geometry. It's just a rectangular prism. And then the bottom is our mesh displacement field. So what happens is when you apply the warp by vector transformation in ParaView with this mesh displacement, you'll get something like this. Here I did have to increase the scaling of the mesh displacement just so it's visible in the slides, but I'll show what this looks like in ParaView right now. Not like that. So we have this reference geometry here, right? And then if we warp by vector with the mesh displacement as the field, we get this. And as I was saying earlier, I had to increase the, let's see, I had to increase the scaling of the warp by vector in order to make it visible. So if we do this, we can see the deformation being applied here. And this is with the scale factor of 100. Let me make this solid color so it's easier to see. There we go. So this is with a scale factor of 100, and you can play around with this, of course. If you just make it 1, it's a lot less dramatic. See? Okay, so to summarize on the sampler, it works with deformed meshes, so with mesh displacement, and you output your reference geometry. You can sample the mesh displacement field and then just apply the warp by vector filter. Moving on, we're going to be talking about online visualization. So it's possible to render models online or through your browser. And the reason we might want to do this is because it's accessible and you can share results easily. Ideally, we want client-side rendering without requiring server resources, and we tested several projects that exist. First, there's Kitware Glance, which is a light ParaView that you can run in your browser. And then there's also VTKJS, which is a low-level TypeScript library that allows you to load, render, and process the models you may have. Regarding the VTKJS, if you want to do a transformation on your model, you'll have to write your own script to do that. So I'm going to just quickly show a few examples in Glance. No. We have this model by Arushi here. And the point is you can just run it in your browser, and you can switch the tab as well, so information. Oops, don't want to. We also have this model by Juliana and Renee, and there's also a video that we can load here. So I pulled up these examples. The reason I didn't click the link here is just because it takes a second to load, so I loaded them earlier. So here's the workflow for Glance. You can load files into ParaView, apply whatever filters you're interested in, and then file, export scene, save as VTKGS, and then you open the Glance file, load it, and then you can save the state and host this .glance file online and make a link to load automatically. So I'm going to show another example where you apply a transformation to your object. This is it. And notice it's rotating on its own. This is a script that Timo wrote that just rotates whatever object you have, and you have to write that manually using the VTKGS. Okay, so next I'm going to talk a little bit about the spherical sampling since there is still time. Uh, so you may remember this image from earlier. This is just a sphere with some prescribed boundary condition, right? If you try to resample this using ParaView's resample to image, you would get these rectangular blocks I was talking about earlier. So that's why we wrote a separate sampler. And this separate sampler, it allows you to sample with respect to r, theta, and phi. And when you apply the sampler, you get this here. This is not quite the sphere that you want, but you can apply the calculator filter with a coordinate transformation, and this gives you back your sphere. So, of course, we don't want to, in the future, have to sample and get this rectangular prism and then have to apply a calculator filter to transform back. But if we when we switch to a netcdf file format, we'll be able to load the structured file with respect to r, theta, and phi directly in ParaView, since there is spherical support for netcdf files. And then another thing I wanted to show is just a comparison between the this is the unstructured file for the mesh displacement example from earlier done by John. And then this is the sampled example. Oh, yes, we had the scaling here that I'll just apply. There we go. So just to reiterate, the top is the unstructured output and the bottom is the structured. You can see the mild differences here. Or I think we can. Yeah. And then the reason we wrote a separate sampler is because once you have this deformed geometry, right, here, if we apply filters, so what happens is if you apply the resample to image filter in ParaView to an object with the deformed mesh, you get these little blocks that you'll see. Maybe I can exit out of this and zoom in. You get this blocky structure again. And that's, again, due to how ParaView resamples. It finds the closest vertices with respect to X, Y, and Z. And that's why we want to generate first a reference mesh and then sample the mesh displacement before applying warp by vector. When you have a mesh that's already deformed and you try to sample, you get these little blocks up here. Back to this slide. Okay, so just to reiterate with the VTK.js, everything has to be written from scratch. Filters are possible client side, and we saw the spinning example that was an object from step 90 in deal 2 that was spinning around. So the conclusions are that sampling from unstructured to structured can save memory. Structured data can render much quicker than unstructured, even if the file size is larger. And online visualization tools can be useful for sharing models, and you can share the videos like we saw. For the future work with the deal 2 sampler, we want to use binary storage instead of ASCII because that just saves on space. Furthermore, in Aspect, we want to be able to sample from the intermediate format directly to a structured sampled file. So PD2 directly to VTI. We also want to have a netcdf output file for our spherical sampling because we don't want to have to do the calculator coordinate transformation in order to recover our spherical geometry. Because remember, when we sampled the sphere, we got this rectangular prism and had to apply the calculator filter to get back to the sphere. If we use a netcdf output file format, we can just render directly as a sphere in ParaView. And there's one more thing I wanted to mention. Maybe here. If you go to this GitHub link, you'll find the sampler, which is a work in progress, and there's a convert PD2 tool, which, given a deal2 intermediate file format, which is a .pd2 file, you can run this to convert your PD2 into a VTU file if you wanted to. You also have the sampler here, and we have implemented so far the support for spherical sampling when it comes to R, theta, and phi. So I went through the conclusions, and here are my references. Of course, thank you.